We are talking today about the zeros of a polynomial. And remember when we were talking about that term, the zeros of a polynomial, that means the solutions, it means the roots, it means the x-intercepts, right? All of those things are the zeros. And yesterday, even though we would factor sometimes, right, it was easy to solve a function when I could factor it. We solved it by setting it equal to 0 and factoring it by grouping. We factored it using trial and error, right? Those are all methods to solving a polynomial. Well, today we're going to talk about how do you go about solving a polynomial that maybe isn't quite as easy to factor. You can't find the factors of it, right? And I asked you to look over that Desmos lesson to refresh your memory on how you divide polynomials, okay? So using long division as well as dividing using synthetic division. So when we cover, we'll use synthetic division today for our polynomials, and we'll use long division when we cover rational functions on Monday. So we need to know how to divide in both of those methods, okay? But what we're going to start out talking about is, like I said, our zeros of a polynomial. So we have this idea, this fundamental theorem of algebra, and it basically just tells me that in short and condensed terms, it's basically just telling you that the degree of the polynomial is going to tell you the number of solutions that you're going to have, the number of roots that you will have. Now, the thing about the fundamental theorem of algebra, though, is it says that you're going to have at least one complex number. I did not put in your Desmos lesson anything about complex numbers. Do we all remember what a complex number is? Imaginary numbers?
Oh, I hate those.
Well, just real fast, remember that it's written as a plus bi, right? That is a complex number, okay? So we generally deal in the real number system, right? The real number system, real numbers being whole numbers, integers, rational numbers, irrational numbers being like pi or square roots, all right? All of those are real numbers. That's part of the real number system. And when we graph on our graphing calculators, or when we graph generally, we're graphing on real number lines. So we would expect to have values that only fall in the integers, decimals, irrational numbers, okay? Complex numbers are the ones, well, actually imaginary numbers are the ones that have the I next to them, right? Those are the square roots of negative values. So the imaginary part is represented by the I over here, all right? And then when you put the two numbers together, they're called complex numbers, because it has a real part and it has an imaginary part. Every real number that you can think of can be written as a complex number, all right? Every real number can be written as a complex number by just putting 0i next to it, okay? So all numbers are complex. We typically only look at the real numbers, okay? But what we're going to talk about, what the fundamental theorem of algebra says, is that every polynomial can be written as a factor, or I'm going to have at least one zero that is complex. Okay, so what we're going to start out looking at are the rational zeros, or the real zeros, and then we're going to add to that the complex zeros that we won't see from our calculator. Okay. So the fundamental theorem of algebra tells us that we have, basically tells me that the degree of the polynomial tells me how many solutions that I have. So if I look over here, okay, here I have the function up there, x to the fifth plus blah, 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 right? That's a fifth degree polynomial. So according to the fundamental theorem of algebra, then I should have 5 solutions. Okay, we talked on the other day, though, that a solution is typically, right, if we're thinking of real solutions, we're looking at intercepts, right, where we're kind of crossing or touching the x-axis here. We know that we're crossing the x-axis here, so that solution in factored form would have to be odd, right? The multiplicity of this root would have to be odd, okay? Here at 1, we're touching it, so that multiplicity would have to be even, okay? And so I could have, even if this is, let's just go to base numbers here. Let's say that this root here is a multiplicity of 2. And let's say this root here is a multiplicity of 1. That gives me 3, right? 3 degrees used up out of a total of 5. So I'm probably looking at 2 more solutions that would be complex, that don't ever show up here because we don't graph complex values. All right, so we're breaking it down into all of its roots today that we won't find just by factoring, okay? Through traditional methods. So that's kind of the overview of what we're looking at. So let's start small and let's start with finding real zeros. Now this box right here basically says there's this rational zero theorem that says if I take the ratio of my p term, I'll tell you what that means in a minute, divided by q, that ratio right there tells me that it tells me what my possible solutions will be. All right, so the ratio of p over q, the factors of p over q tells me what that is. Now, where does p come from? P comes from the constant at the end of the polynomial, and q comes from the leading coefficient. That's all you basically need to know for that part right there on the rational zero theorem. Where does the p come from and the q come from? P is the constant at the end of the polynomial. Q is the coefficient on the leading term. Okay? Now what do we do with it? Well, I'm going to show you how we apply that here. So the first polynomial that we want to find the zeros of, and we're looking for just the real zeros on this, is 2x cubed plus 11x squared minus 7x minus 6. All right, that's the polynomial that I want to look at. So let's kind of get a feel for how many solutions I might be looking at here. So this is what degree polynomial?
This is 3, right?
So it's a 3rd degree polynomial. I should have at most 3 roots. I would expect to see 3 roots. Now we're going to only concentrate right this moment on the real roots, or rational roots, I should say even. No imaginaries are coming into this right now, okay? Now the next thing that we're going to do, if we're thinking of steps here, right? I want to determine the potential zeros of this function, and it comes from that ratio of p over q. So I'm going to take the p value, and I am going to write it out all the factors of 6, the plus and minus factors of 6. So that would be plus or minus 1, 2, 3, and 6, right? Those are all the factors of 6, plus and minus. Then I'm going to find all the factors of q, plus or minus 1, and plus or minus 2. So first I've got to write out the factors of p and the factors of q. And from that list, I am going to create the list of potential factors, which comes from p over q. So p is in the numerator, q is in the denominator. So I've got 1 over 1, which would just be plus or minus 1. I have 1 over 2, right? The 1 here over the 2 here, right? So that'd be plus or minus 1/2. Then I have 2 over 1, which is just 2. And I have 2 over 2, that's 1, correct? So I don't have to use that one. Now I do 3 over 1, 3 over 2, 6 over 1, and 6 over 2 is a repeat, so I don't have to use it. So right here, I have a list of all the possible real solutions, roots. These are all the possible roots, plus or minus 1, 1/2, 2, 3, 3/2, and 6. These are all numbers that could potentially be roots, okay? And hidden inside of this list is a root. So from that list right there, in the olden days, back when I used to have to do this, I would have to take each of these 1, 2, 3, 4, 5, 6 times 2, 12 possible roots here, and I am going to plug it into the function, because if it's a root, it would be a factor, right? If it's a root, if I plug in for x, I should get 0, right? That's what our root tells us. If I can replace it into the function and get back 0, then it will be an x-intercept, won't it? Okay, so there is a list of all the possible x-intercepts right here, okay? And you can take it and you can plug it into that function 12 different times and make a list of all of the ones that came out to be 0, because that is a solution to my function. But that is not the way that we're going to do it, because we have technology nowadays. And so what we're going to do is we're going to let the calculator do the grunt work for us, I say. All right? So in our calculators, we are going to put that function, all right? So we need to go to our y equals I've got my plot on still, so I'm going to turn that off. I'm going to get rid of the function that was on the y1 to begin with, and I'm going to add the function we were just looking at, which was 2x cubed plus 11x squared minus 7x minus 6. And now I'm going to, remember we had that table function that we were using the other day, right? Do I have it in there, right? Yeah? Did I enter it in there, right? 2x cubed plus 11x squared minus 7x minus 6. Okay. So that list of p over q's that we were just looking at, right? The long list of 12 numbers. The very first one was positive and negative 1, correct? So I'm going to go to my table. I'm going to go to my table, and I already had that in there from when we were working the other day, but if I were to enter the number 1 in there, I get back 0, right? I evaluated the function at 1, and I found out it was 0. That means that's an x-intercept, correct? So I've got my first number, okay? Instead of me having to manually test these values, I'm letting the calculator test the values for me, okay? Now, you could continue on with the list, but that's going to fail you whenever you start finding numbers that are not integer values, right? This will only work in the table for these integer values. So we're going to have to start imparting some of our algebra. So I know that I have a solution at 1. So coming back here, I'm going to write that down, that I have a solution that we found from our table at 1. And I'm going to use that to now divide into my polynomial function. Okay, so I'm going to divide it into my polynomial function using synthetic division. So synthetic division says I'm going to take my solution, or my root right there. And remember, I have my little upside down house right there. And I'm going to take each of the coefficients from the original function, 2, 11, -7, and -6, and I'm going to divide in there. So we start by bringing that 2 down, and then we multiply 1 times 2, which is 2, and we add, giving me 13. I say 1 times 13 would be 13, add straight down, and I get 6. 1 times 6 is 6, add straight down, and I get 0. Now I always box in that last term over there to remind me that's the remainder position, right? You all did a little graphing where you have some remainders, right? Okay, well, if this is a factor of my polynomial at the top, then it should divide evenly into my polynomial. That's kind of a rule, all right? So we already know it's a factor. We verified that using our calculators, okay? But if it is a factor, then it should divide evenly into the polynomial. And therefore, the answer when you do synthetic division is always going to have 0 here. If you don't get a 0 here, you did something wrong, okay? Now, so we have this. Once I divided my 3rd degree polynomial by x, I end up with x squared as a polynomial, right? I'm going to create, in other words, the result. Let's rewrite our polynomial. Let's rewrite my division here. This looks like 2x squared plus 13x plus 6, correct? That's how we would fill it back in? Yeah?
Yes, ma'am.
Okay. And I already have a set of factors of x minus 1, right? That was another factor that we had, correct? X minus 1. So what I have here so far is a partial factoring of my original polynomial, okay? So I've broken it down so far into the first root of x minus 1. I have this right here, which is a trinomial, 2x squared plus 13x plus 6. And the next question you want to ask is, can I factor that? Right? Can I factor this trinomial? That's where we're looking at right here. And factoring being, could I use trial and error factoring, or could I use the quadratic formula? We'll see that in a minute. So it turns out, yes, I can factor this trinomial. That's going to factor into 2x plus 1 times x plus 6 times the x minus 1 that I had. And I now have broken this polynomial, the 3rd degree polynomial up at the top. I've broken it down into a product of its factors. Think about this for a second. If I were to look here at this one factor, x plus 6, that would have a root at -6, right? That is a value from the list from the top, isn't it? How about this one over here, 2x plus 1? If I solve that, I get x is equal to -1/2, right? Okay, so that is also a value from that list up there, okay? This example that we're looking at, you could have just done it from the table and found out where all of those zeros were at, and that would have been great, right? But we're practicing how to do this for when you can't find zeros off of a table, okay? So the idea here is you take your polynomial at the top, you list all the possible roots, and you find the very first one using your table. And from there, you you do synthetic division to break it down into its roots, right? Into its factors. So here, as I have it written down, is the polynomial in its factored form. If I wanted to know now what its roots were, how would I solve it for its roots? Set it equal to 0, which is what we did the other day. 2x plus 1 equals 0, x plus 6 equals 0, x minus 1 is equal to 0. Just like I was saying, -1/2, -6, and +1. So there's two ways I can ask you a question. I can ask you to find me the roots of the polynomial, and you would do it this way. I could ask you to give me the polynomial in its factored form. Those are just two ways to be able to ask this question. All right. Questions on that? That's kind of easy. Let's do one that's a little bit more complicated. Here I have x to the fifth minus 7x to the fourth plus 19x cubed minus 37x squared plus 60x minus 36. So what degree polynomial is this?
Fifth.
Fifth degree polynomial. We're looking at, we could potentially have 5 roots. Now let's make a list of the factors for p.
P is 36. Isn't it?
P is 36. So I've got a long list here. 1, 2, 3,
4,
4,
6,
uh-huh,
12.
9, uh-huh, 12, 18, and finally 36.
Wow.
It's a lot. Q, however, only has plus or minus 1. I always like that because then that means that the potential list of P over Q is simply all the P's. Okay, so that's, looks like a lot, but it's not as bad as you think. So we're going to take this function and we're going to put the function in our graphing calculator. Okay. And when I put it in the graphing calculator and I graph it, I can kind of see what's going on here, right? This is a similar problem to the one that we opened with. So I get kind of a feel for what's going on here. So when I go to the table and I'm looking at the table, maybe, and I put in your first root, which we can see there from the graph, but you're going to put the first root in and you're going to find that the first root you found was at 1, correct? Did you all find a 0 at 1 when you put it into your table? Yeah? Okay. All right. So I have one root at 1. Let's do synthetic division then on that root, using that root. So I have 1, -7, 19, -37, +60, and -36. So we're going to keep doing our synthetic division on this. Let's get down to the end. We'll all do it. 6. Positive 36. Thank you. So do you get 0 when you get to the end? All right, you did it right then. All right, so I have these for my coefficients. Now, does this look like anything that I can factor yet? What degree of a polynomial would this be that we just found? Fourth degree polynomial, right? If we started with an x to the fifth, we divided it by x, we ended up with x to the fourth, correct? Okay, so we can go back to our list here, all right? And I can divide another number in. I don't have to divide it into this, because if I have a root, it would evenly divide into both the original one and it would divide here, because they're all factors of each other. So go back to the original list, this potential list of p's over q's, right? Find me another root that divides evenly into our original function. What's the next one that you find? 3, right? Didn't 3 divide evenly in there? Okay. So now I'm going to take my fourth degree polynomial and I'm actually going to divide it by 3. Okay. So I did synthetic division again. I end up with these terms right here. So I'm now down to what degree polynomial now? I'm in a third degree polynomial. So what I have here, how many terms do I have? I got 4 terms. So let's kind of take stock of what we've got here. I had x minus 1 as one root, x minus 3 as one root, and I've whittled this thing down into x cubed minus 3x squared plus 4x minus 12. You could go again if you wanted to, or we can stop here and we can see if I can factor this third degree polynomial, because there's 4 terms. Remember we practiced factoring by grouping yesterday? So I can try to factor this by grouping. So if I take my fourth degree term here, or excuse me, if I take my third degree polynomial here, x cubed minus 3x squared plus 4x minus 12. I just rewrote it so that we can see it a little clearer. Remember when we try to factor this, I'm looking for what I grouped it. What can I factor out of the first set of parentheses? Okay, so that factors into x squared, leaving me with x minus 3. And what can I factor out of the second set of parentheses?
4.
Okay, so that leaves me with, again, x minus 3. That factors then into x minus 3 times x squared minus 4. Excuse me, yeah, plus 4 things. So my this chunk of the polynomial, right? That part right there, all 4 of those terms factored into x minus 3 times x squared plus 4.
Can you now set them to 0?
I could if I wanted to, but I'm going to finish this off by bringing down those 2 factors that I already had. So I had an x minus 3 already, and I have an x minus 1 that we found already.
Could we combine the x minus 3s?
We could, if you want, x minus 1, x minus 3 squared,
Yes, ma'am.
x squared plus 4. So we have 2 roots that we could see from the graph, right? One of them was occurring at 1. It had a multiplicity of 1, so we crossed at that point, didn't we? We also had a root at 3 that touched it, didn't it? Right? It touched it. Okay, so it had a multiplicity of 2. Here's the last root that you never would see, right? This is the last factor over here. Okay, x squared plus 4. Can I solve that? Why? Right. Okay, so if I were to solve it, I would not get a real value. Okay, because I would have to subtract 4 to the right. That would be the x squared equals -4. So just like Isaiah said, it would be imaginary. Okay. A couple of things about this. When we look, because you're using the graphing calculator to begin with. Okay, when you put the function into your graphing calculator and you use the table to find the roots, it's helpful to kind of see what's happening at your root, for you to kind of anticipate what's going to go on at that root, right? So I know that I've got something here that would be odd. I know I've got something here that would be even. The even values, I guess maybe the odd ones too, but I usually think of it more in terms of the even ones. Those are the ones where I could have used that same root of 3 and divided it one more time into here using synthetic division. It would have been the same concept, right? Because I can use it twice in this. It's a repeated root. So it factors in, it would be in there, involved in it twice. Okay, and you can see that if we are looking at roots, the roots are the things that are all multiplying together to give me back what I started with, right? So that's how come I didn't have to. I can always go back to the original polynomial and just keep dividing my list back into it. Okay, I don't have to redo anything to divide it into. Questions on that? No? All right. Now let's talk about the complex ones. So complex roots are going to always occur in conjugate pairs. So we have to kind of think about that for a minute. That's what that says. Complex roots occur in pairs. So if you have an a plus bi as a 0, then you're also going to have the a minus bi. Remember, conjugates are the same thing, just different sign. Okay, so let's practice that for just a second. And if we're thinking back to the picture that we were just looking at, right? This one right here, where we knew we had one root at 1, we had 2 roots here at 3, and we know that we had x squared plus 4, right? So there's 2 roots that are remaining of the 5th degree polynomial, because we're going to use all 5 of them in this. When we can write them, when we can write the entire polynomial in its factored form. In other words, if I'm going to introduce imaginary solutions into it, then I will have the number of roots equal to the degree of the polynomial. Okay, so we would be looking at, since I want to know all of the solutions or all of the factors, we have 1, 2, 3, and then we've got 2 imaginary roots, which would be the 4th and the 5th root. That's what we're looking at for those complex, for the conjugate pairs. So if I know that I have this 5th degree polynomial who has a 0 at -2, at -3i, and at 2 plus 4i, what are the 2 remaining roots? Based on the conjugate pair theorem, okay, everywhere that I have an imaginary number, I'm going to write its conjugate. So at -3i, I would also have a positive 3i. And at 2 plus 4i, at 2 plus 4i, what is its conjugate? What's the conjugate of 2 plus 4i? 2 minus 4i. Do you all understand what I'm saying when I'm saying conjugate? No? So the conjugate is simply the same, it's the imaginary portion with the opposite sign. When we multiplied by the conjugate using our identities, right? It was that binomial, same thing, only opposite sign for the second term. That's what a conjugate is. So here I've got 1, 2, 3, 4, 5. I have all 5 of the roots now for this 5th degree polynomial. Okay? It's the real portion. So the conjugate pair theorem is really only talking about the imaginary guys. Okay. Okay. So let's look at this example here. Although this says find the complex zeros, read the questions very carefully when you're working the practice problems, because it will ask you to find the real zeros. That's what we just did. Okay, we found all the real zeros. If it asks you to find all the zeros, now it wants everything, complex and real, okay? So it's kind of confusing when they're both in the same lesson, but. So we have x to the 4th plus 2x cubed plus x squared minus 8x minus 20. This is a what degree polynomial?
4.
It's a 4th degree polynomial, so we're looking for 4 roots. Because I want to know all the roots, I am in fact going to be finding 4 roots. So we do the process the same way though. We still list the potential zeros by taking the factors of p, plus or minus 1, 2, 4, 5, 10, and 20. Those are all the factors of 20, right? All the factors of q, which is just plus or minus 1, makes it pretty simple. So what are my potential zeros that I'm looking at? All the values of p, right? Okay. So now go to your calculators and we'll put that value in.
You forgot the plus.
Okay, thank you. Is it right now? Yeah. So what's your first root that you found? 2. Okay. Did anybody find a different root first?
-2.
-2. Okay. Now, it doesn't matter which one you find, right? If they're both roots, it doesn't matter which one we use. Okay. I'm going to use +2, or excuse me, I'm going to use -2. So -2 divided into that. So I have this from a 4th degree polynomial down to a 3rd degree polynomial. So x cubed plus x minus 10, I wouldn't be able to factor that using grouping. Okay, so now we're going to go back in and we're going to try the other root that you all found. We know that there's another root at 2. So I now have this factored down into a 2nd degree of x squared plus 5, right? So I'm just going to rewrite my list of factors that we have found so far.
I thought it was 2.
Oh, I didn't do it right. Yeah, you're right. 2, 1, 2, and 5. Thank you. Before we got too far. So I have x minus 2 that we started with, x plus 2, and x squared plus 2x plus 5. Now, I can look at this. This is a leading coefficient of 1. So I'm only concerned with the factors of 5 if I'm thinking trial and error, because I can do this in my head. Are there any factors of 5 that add to give me 2? No. No factors of 5 will add to give me 2. That means that you have to solve this using the quadratic formula. Okay? You can't use trial and error. That doesn't mean the solutions don't exist. It just means we have to use the quadratic formula. Remember, the quadratic formula says -b plus or minus the square root of b squared minus 4ac all over 2a. So -2 plus or minus the square root of 2 squared minus 4 times 1 times 5 all over 2. So I have a -2 plus or minus underneath the radical, that's the discriminant. Remember, we called that the discriminant. So I have 4 minus 20, so I would have -16 over 2, -16 under the square root sign over 2, which is -2 plus or minus what? What's the square root of -16?
16.
4i. Square root of 16 is 4. So plus or minus 4i over 2. And I can simplify that by saying -1 plus or minus 2i. -1 plus or minus 2i. Okay? Are you all good with that? That's all the complex numbers we need to really be dealing with. Are you all right with us doing that? Okay. So now this is how I would rewrite my function in terms of its factors. I have x minus 2 and x plus 2. So before I write any more, how did I get x minus 2? How did I take its root and write it in its factor form? What is it? What is the process? So when I put it back into the factored form, it's always going to be the opposite sign of what I had, right? Of where the root would be. So it's always going to be x, there's your variable, minus then the root, okay? So what this looks like is x minus a negative or plus 1 plus 2i, and x plus 1 minus 2i. So just deal with, pretend the I part isn't even there. And if I were to rewrite that, it would be x plus 1, and then tack on plus 2i and minus 2i to the two more roots that you found. Okay? So that is the function in its factored form. So again, you would only see when you graph it, you're only going to see these two roots here, right? The real roots. Those are the two roots that are going to appear. Now we've only worked, and you're fixing to work 4 problems on your own as practice. We've only worked roots that are integer values, okay? But I could have solved using the quadratic formula and found out roots that were irrational or square roots. Those are still real roots. They would appear on my graph, but like the square root of 2, I think is 1 point, what is the square root of 2? Square root of 2 is some value, right? Some decimal value. Yeah, that decimal value, you're going to see it as an intercept, right? You're going to see it as an x-intercept, but you won't know what that number is, in other words, right? Those are called irrational roots. All right, you'll see what I'm talking about in a minute. There's 4 problems that I want you to find the roots for. Problems 1, let me just make it a little bit easier. That's the only one I want you to find all of the roots for. Okay?
So we do all 4 of those?
Yep, do all 4 of those. Okay? Ask a question, use your neighbor, be fine. Practicing what you did. And then you plug in find one. Here's your first one. So you're going to plug in +1, and then it's going to spit out the number. And if it's not 0, you go to the next one. So you're going to try +1, then -1, +2, -2. You could use, you can use the Desmos function on your cell phone. Okay, I do have the Desmos. The reason mine didn't give me that table is because I have multiple functions listed there. So I had all of them entered in there, and the reason it didn't give me a table is because I had too many things labeled as the same thing. I'll show you in a minute. I'll show you. All right, Jimmy, you're needing the rest of that, aren't you? There you go.
Oh.
So this is where you're going to enter.
First.
Oh, you have the next one.
And then whatever you get here, we add 2 zeros. And then just kind of here, next step. Here. 0, 0. And 0, 1.
Once we keep finding the x-intercept direct on the existing wall.
2, 2.
Yeah.
This only really
Get-
if it even could. Because if it didn't.
Okay, so
You know. That's what.
3 halves.
It's only words for whatever one you think.
Yeah. Oh, it's 3 over 2. Okay, but make your list. What do you got?
So I've got P is 1 and 3, right?
No. Yes, P is 1 and 3. And what are the factors of Q?
It's 1 and 2.
It's 1 and 2. Factors of Q are 1 and 2. So P over Q is going to be 1 over 1, 1 over 2.
Over Q is 1 over 2.
And then 3, and then 3 over 2. And all of those are plus or minus. And you don't
So we
just-
basically plug them in.
Right, that's what I did.
Okay.
Are you plugging in just the P values or the P over Q?
It's P over Q. Whenever Q is 1,
Yes.
then we only have to use P.
Okay.
One.
Also, I'm.
You got it, Andrew?
I was
wondering what else you did.
This is the factors of 3. Factors of 2. And then you write it as a ratio.
That's it.
Yeah.
If it's just services.
So on that, just like on our graph we have here, I can hit the gears off. See the table appears, and now I can check out. You just type over.
It's 2x.
Isaiah, did you? Can you use the table on your desktop?
Yeah, I'm still right now. Well, you're doing.
Okay. Okay, yes, those are the lists, that's the list. And you put the function in your graph, right? Yes. And it's waiting on you.
I think it's legal like that. If you can't.
Just, you gotta keep going through the list and it'll define lines that work. Yep.
Just leave it like that. That's the answer.
Keep going until you find it.
Yeah. So I think we should- Yeah, it's not-
So it's also nice if you just put table, graph with us. I said, let's do Zoom and change it back to your standard, so it's 6. We'll do the 10 by 10.
Yeah,
Now
no,
you can
it's
see,
too much smart.
you've got 1,
Because
2,
you gotta-
3 roots that are gonna happen.
You're trying to
there.
change
They're
it
just
back,
not
so so you multiply by 3.
gonna be.
Is that? Or that's it? Or you leave it like that?
No, I want it simplified.
So it is.
You can't factor it. This is the one I was telling you about. You can't factor it, right? So the first one, right off the bat, right there, that one's gonna have an irrational root. It's gonna have a square root. Find that by quadratic formula.
So how we set the long division this?
We don't do long division.
Not long division, this static one, because x is equal to 1. So we.
Okay.
Because we got one of the tables. 1 and 1 and a half. It's 3 over 20.
One, you need 3 halves.
Yes, ma'am.
All right, so put
Wait,
3
how'd you
halves in.
get minus?
So we divide.
Oh, okay. Yeah, yeah.
Multiply by 3 halves. It's not bad. It's not gonna turn out bad. Write down
What does
the, write
that
down
mean?
the,
Negative 16?
the thing.
Just be negative.
2 times 3 plus 7, which would be negative.
What did you choose?
So simplify.
So that's a negative.
Minus
You really should go
4
back.
AC.
You can't do this,
Negative.
no. Because if you
Oh.
you would need a 4 on the outside of that square root.
Yeah.
So secret is
So then we'll do this in reverse, and
I
so
have
2 times negative 2 times negative 2 times negative.
You're right.
That's what I'm doing, that's 16.
So it's 32.
Simplify that.
You can do that. Square root of 4 times square root of 8.
one,
So then you end up with 2 square
that's
root.
not square root 24. is the same as square root.
4 square root.
So simplify square root 24 are not better.
Minus 4 square root of
Okay, so we set our table.
So it should be
Calculator,
1 plus or minus square root.
your calculator is.
Yes, right.
We don't want to do that. Instead, I want to show. Arrow down to R, arrow over to app. Uh-huh. And this is why, because currently it's set to start at 0 with a change of 1. So that's how come you put me down. Right? And I'm not gonna mess with. I'm trying to help. So, hold on.
One
Eight.
plus one.
No, I know. And it's weighted. So you put in plus 1.
You gotta put the X in.
And
X plus.
I think it. Oh,
Oh, yeah.
and then if plug 1 into whatever's on Y1. Which is your equation. What do you do? Find zero.
It's just square. So you end up with -4.
I doubt she did that. Still is fine for.
Now,
Wait,
really
okay,
quick, let's change your graph
And I
Go back to
knew how to do.
and change it to
This
the
is
standard.
simple minus 2.
It changes it to the 10 by 10. We had it adjusted.
Yeah, my shares fell.
So you can see here that we're looking at three roots. It is a third degree polynomial. You should have two factors. Because I can really see it properly, the real number line.
And then.
The trick to this one is they're not, this is your
I
own.
looked at it.
It's just.
The others are going to be
Not the
square.
same thing.
Did you get it?
Yeah.
Yeah, that was right.
So, another one is.
Final answer.
Ah,
Yeah. Which one is doing that? So I did it all.
But it's under my name.
Well, my calculator actually.
Can you just specify something?
Yeah.
We'll still leave the remainder. -8. Stay.
Oh, no, it's 4.
Yeah.
But how do we? We don't have a letter. It's gonna work.
But we want to check.
With all the rooms, with all the-
Yeah.
So you write your 2 down.
Yeah. Another word.
Or you have times 4, which is-
I'm missing. One, two.
Plus 1 plus square root 2 plus 1 minus the square root 2. That's right. Okay. Did you get?
But I think that's why.
Yes.
Yeah, I just immediately ruined it for everybody.
Yeah.
I didn't want to mention it, but then it like fell out of my mouth.
Okay, so it's -1.
So I agree with this. This
So.
isn't right. This is right. Negative b plus or minus b squared minus 4c all over 2.
Good calculator.
So.
-1, -2.
This one? So practice writing it as a product of its factors. Yeah. I'm not gonna do that homework. You know, the first one, there you go.
Honestly,
We do that.
so,
Oh, so this is- no, so this is quadratic,
so basically we get this, back on here.
right, but I can solve it
Do the
using
quadratic
quadratic.
formula.
And I'm looking for, can I solve it using the quadratic and find real numbers? Not imaginary.
Spoiler.
Well, because I already told you.
So, yeah.
Negative p on the outside. The negative b, so
Oh, no, it doesn't.
negative
No.
4, right? Plus or minus the square root
So I got
of b
1
squared. 4, right, 4. Minus b squared minus 4. 4
Oh, no.
times a times b.
Are
All
you?
over 2a.
X minus 2 squared, right?
A is going to be the first number here. And the sign code is the number. Okay?
That's nice.
Like, I saw this.
This is an-
No, you're right, you're right.
The one that I did.
Oh, I'm looking at the wrong one. I'm not gonna-
No,
You're right.
you.
Right? I did.
No, I understand why.
What I did. Or if you don't.
Yeah.
Yeah. You just have to keep
You guys.
not written, but I did.
There's a reason why.
Got it, did you get an answer?
Professor.
All right.
It would be like.
All right, Mommy, what?
So would this be, will this be correct?
C is a negative.
Plus
16 plus 16.
32. And then, so then I did divide it. So then I did divide it. Oh, I don't think I have no doubt in my
So
mind.
simplify, square root of 32.
Oh.
Square root of 32. Square factor. You told me what I did. Yes, you can always check that.
1, 5, 17,
You can always check it by going.
Technology.
How do you simplify the square root of 32?
Divide.
I want you to simplify it. Well, that's for first, right? So how do you know it's? You look for perfect square.
I did it.
I want a perfect square factor. So I'm not- Four is a perfect square, but it's not big enough. It's 4 times 8, right? I want go bigger. So it's not 16 times, so I can take the square root of 16, and 2 stays underneath.
So should we just leave it like that? Like,
You get.
yeah, so now we have. Yeah.
X 57 minus.
Oh, it's negative, that's.
Well, when we go from the solution and writing it in its factor form, if I were to set x equals 0, solve it, I would add 1 to the other side, right? Well, we're doing is going back, starting with solve.
There's no factors.
This x, so if I solve that, I would add 2 to the other side. So I would say x equals 2, that's that one.
So we're gonna have.
This one, if I solve it, x equals negative 2, right? That's that one. X is equal to, so x is equal to 3 halves. Now move it back over and join it. Just doesn't matter. You gotta use the quadratic. As irrational fruits. How did you get?
You can simplify.
So it's, we're using this right here, right? This is the trinomial we're trying to factor. So we're trying to figure out what it's. So.
Oh, I see what I did. What'd you get?
So what's A, what's B, what's C out of this? Remember, that comes from AX squared plus BX plus C. That's the general form of the quadratic.
How'd you get -2? Because you can't divide. What?
And the signs
When you get
say.
Oh, shit.
Or 8.
I thought it was 2.
Oh, it is 2A.
Yeah.
Oh, so we got one. So just be plus or minus 2. Negative, no, negative 1 plus or minus 2.
That's the
What if I did?
Yeah, it comes from general form of a quadratic,
Because
ax
it's 2B.
squared.
Two A.
Oh, it's 16 in it.
Ax
It's two A. Volume is two A. So 2 times 4 is. Yes, our A is 1. So it's just 2.
It's simplified, and that's where it's.
Negative plus or minus 2.
2 I. Because it's
Can
a
I factor
negative
x
square
squared
root,
minus
so you
4?
can go, it would be plus minus 4I.
So there's two terms
What's the
separated by a minus
Two,
sign,
right?
that's
So
good.
you get 2I. Because
Yeah,
the 4
the
is
first and the
negative.
last terms are perfect squares.
Whenever you have a negative, you can't take it out unless you take it out.
Oh.
So how many of them do you want to have?
Right?
That would be a repeating.
Negative A plus minus 2I.
Would be X.
You get
Minus
I.
Nothing plus
Oh,
square.
look at
X
that.
minus 2 quantity squared, right? So you should have 3 places it crosses, and it would be bouncing back off from here.
Or X minus, or X plus 4.
Oh, you've already got it in.
Right.
Yeah, so you can see, you touch, cross, and you cross.
You do 30 minus X cubed.
Oh.
I just gotta find it. When did you get it?
X plus 5, X plus 5, and then X plus 1.
Are we doing this one over here, the complex?
No.
2x cubed minus x squared plus 2x minus 1.
X cubed.
Okay. And you've got plus 5, plus 4, plus I, plus 4.
Yes. There we go. That's right.
Did you get it simplified? Yeah. And now, as long as the denominator goes to both of those, then you can simplify.
Did you get this answer?
Yeah.
So, okay, let me rephrase. What does it matter? If you find that you get a little messed up on those fractions or using it was 4 plus or minus 4 square root 2. Is that right? In the front? So this is negative 4 over 4 plus or minus 4 square root 2. They're 2 separate fractions, right? This is negative 1 plus or minus. Oh. Is that where you were going with it? Is that what you got it?
Yeah, I got that, but, I'm confused if, whenever you write history, you're getting to me, it's 3 over 2, so I can do that, and then, since it's so plus or minus for some.
So you're gonna have 3 factors there, right?
3.
Yeah, because you found 3 roots, didn't you?
Yes.
You found the 3 halves as a root. We have this plus, and then this minus. So there's your 3 roots that you should write.
No, 2x squared. Oh, no.
So that's.
I really. What's the name? No, it's fine. I was just playing.
What did you get?
We get the same answers for the first two.
Well, not 2 2s.
So he was judging these super.
Yeah, I was gonna say, because we.
I know, and I and two answers.
Oh,
They're
okay.
both complex,
Oh,
right?
I was like, okay, zero. Two eight.
Oh,
How is that zero?
also doesn't mind.
Square root. Plus minus four. Plus minus two. One out there. And then
Two X. X.
yeah, two X.
X minus one. X plus I, X minus.
But when you usually write that as two X minus one. Since you want to get it.
This is there was no there. This is the two.
So my grandfather
Oh, there we go.
had eye cancer. He had his eyeball and his eye really. And I remember seeing it. Yeah, because he was 78, he didn't really want to wear an eye patch. So there's like, I think they grafted it, but it was like a hole with skin. And never forget, because and he had the coolest prosthetic though, that, so you know, he's 70, he's got the eyes, they look almost exact when he would wear it, he didn't want to wear it, so he just usually wears glasses, like a slide on top of it, but. So it was always nice. Well, and then when he did have that, he was sitting on one side and he hadn't seen him for a while, right? There's like a hole. Then, so I was in college and came home to visit and my grandparents, his grandmother had Alzheimer's. And so she would wander around. She could get kind of angry about certain things. She was confused, right? So I'm in the house. Kind of upset about something, so I went outside. I wanted to go outside.
Yeah.
So I go outside, and my grandfather is laying there by the pool. And so Paco had laying there, he had his teeth out. He looks up at me, he has no eye anymore, and he's got his speedos on, and I was just like, I'm going back to school. I'm leaving. I had enough of this. And I know, I had my grandmother. It's Sunday, so I said, it's time to see you, Mom. I'll see you later, Mom.
Seriously, I was like.
No, it's fine. But he was like 80, he doesn't. Right?
He's living his best life.
And I knew he had one over there either.
Because he didn't leave.
You done?
Yeah. Complex.
Yeah.
X minus one half X side. I like this better than the
Which part?
rest. All of it.
You trick?
Especially because.
The identities or the solving equation?
Whatever-
Better just
whatever
suck
was-
it up and get over it.
whatever was on the
Get all the
base.
equations.
Whatever was on the base
You mean the test?
and the test.
Did you practice?
Trust me, I stayed up those.
More than what, the night before?
No, it was like the 3 days before,
That's still not enough.
till like 1 in the morning. But I just think it's.
Should just always be stuck.
Because I did the same thing.
I'm still practicing.
That's the method.
So actually, this would be a repeat. Go back to the-
Oh, no, it's just,
Yeah, but I'm failing classes.
So I need to stay. Yeah, well, that makes sense. Makes sense. It makes
Good try.
Now, this, so I can use my table and I can find all the.
You know how an interesting view we have our own.
Here.
They drop our homework.
I mean, they do. If I wanted to know what the decimal value was. I can find that, but that's not exact. Yes, and they're nice.
Oh,
The
they had like
numbers like
so
I
many.
just found in the table.
You showed it for the grade.
Yeah, no, I'm not talking about, you know that one time.
I forgot.
What did we get?
Like we did it.
I got.
So, we have negative.
I think it's so.
Right, so I have, we started with a.
We're in sync with only the.
Yeah,
Don't you have a
yeah.
That makes more sense now, because I would have did this because you had a quadratic, now you have a. So at this point, you can divide into it. You're trying to whittle this thing down.
Back to the south.
You could stop here and ask yourself, like, back to the. I have two books and I have a word.
Yeah.
Yeah, so that's what I wrote up here, right? And I factored.
I'm sure.
I'll get through it.
I got one of them.
Because you know exactly. So now I'll take another one and I'll like, you already know it's. I'm ready to go right
I'm not built for that.
Posting a special. Yeah, I wonder.
Yeah.
For me, it's becoming more. I can literally. That's why. Yeah, I never mind. And then it's separate.
Okay. Then you're doing great.
So cheated the first half.
So we're just adding an X to these.
Yeah. If we did it, I'll get rid of it. So it's like, you don't do it.
Oh.
No, I actually gave it all. I didn't show it. No,
Put that equation in two.
Hold on. I did it. I should know.
Since I didn't, well, I did.
Yeah, I don't know what happened.
That's what happens.
Actually, it would be actually. Should be able to. Were you gonna put the first two numbers together? Okay, so second two numbers. Be careful, you cut off a negative sign. All right, and then factor a GCF out of each of those two groups. Right, that's how we do it. Okay. Some of you are done, and so I just want to say real fast, and the rest of y'all keep working here.
You have practice problems over this that you should be practicing on, right? This work that we did in class is not sufficient to understand how to do it yourself, all right? There is a Desmos lesson that I posted already that is talking about the understanding of what we're doing today. So it's more conceptual, I would say. So that lesson is up there. And then what else do we have? Then if you go to the dashboard, I already had a lesson up there that we'll cover on Monday, a Desmos lesson that we'll cover on Monday, okay? So we're done talking about polynomials, and when we come back to class on Monday, we'll talk about rational functions, okay? And graphing rational functions. So this is very important. These polynomials and these rationals is the very first thing that we will be doing with our derivatives when we get into calculus. All right, so we're kind of brushing up on our algebra and what these things look like as we move into the next one. Now, if you're finished and you've checked your answers with me for these 4 problems, then you're free to go, and I'll see you back here on Monday. Otherwise, keep working for a little while longer, and I'll be happy